Okay, let's start lecture 1.6. We're going to look at other types of equations and one application. We don't have too many problems to go over, but each problem requires several steps, and the algebra behind them might be new to some of you. If you had intermediate algebra last semester, you will remember it, but for those who are a little bit shaky, we'll go through this step by step. This chapter actually covers quite a few things. So the first thing I want to define or remind you of is a rational equation. So a rational equation is an equation that has a rational expression for one or more of its terms. So a rational expression, what's that? It's a fraction whose numerator or denominator, or of course both, are polynomials. And for this class, they will always be polynomials in a single variable of degree 2 or lower. So notice a regular fraction, 3 over 4, is actually a rational expression because 3 is a degree 0 polynomial, 4 is a degree 0 polynomial. But that's kind of the trivial case. We're actually going to be looking at polynomials in a single variable of usually, I think always, at least degree 1. So to solve a rational equation, we're going to use the trick that we always do. We're going to clear the denominators by multiplying both sides of the equation by the LCD of the rational expression. So the result of doing that is you're going to get a new equivalent equation with no fractions, no denominators. You clear the denominators. If the resulting equation has denominators still in it, then something's gone wrong, and that usually means you've not multiplied by the correct LCD, or equivalently, you may have failed to cancel like factors that appear in both the numerator and the denominator. So here I'm going to, I'll do it here in just a second. I want to go I'll do it right now. So when we look at and we try to find the LCD of polynomials, I want to show you a linear polynomial. It's a degree 1 in a single variable, to be specific. So it has the general form of ax plus b. For example, 7x plus 3. So linear polynomials, they are prime. I'm not done with my sentence yet though. They are prime if the GCD of a and b equals 1. So this is a prime polynomial. What's a polynomial that's prime? It means it can't be factored. So the GCD, or if you want to call the GCF, of 7 and 3 is just 1. Remember the GCD, the greatest common denominator, or the greatest common multiple, is always less than or equal to the smallest of the two numbers when we're talking about regular integers. And it's always equal to the smaller of the two if the smaller of the two divides the larger. So in this case, that's not the case, so it's 1. I'll give you an example of a non-prime linear polynomial. 12x plus 3. Well, the GCF or the GCD is 3, so I can factor out a 3, and that gives me 4x plus 1. So this is not prime. Now for degree 2 polynomials, you're going to try to factor them. And if you cannot factor them, then they're prime. So that's going to be important when we're trying to find the LCD of polynomials, denominators which are polynomials. So let's go on to the next thing that I have up here, the division by zero warning. So as you've heard a million times, division by zero is undefined. And when we have a rational equation where the denominator has a variable term, which is either to the first or second power for our class, we always have to find what values make the denominator of the original rational expression 0. Many times we can find that by just looking at the LCD. And once we find that, we exclude any possible solution values that make the denominators equal to 0. So we're going to just, what the heck? I did not know I could do that. That's kind of cool. I don't know what I did to do that, but I did it. Okay. I think I pushed on that right there. That would be the obvious thing. So let's look at this first example. So this is example 1a. So we're going to solve, and this is our first objective. These are going to turn out to be rational equations that lead to linear equations. So notice that this is a rational equation. There's the equal sign. And in this case, we actually have two rational expressions. Here we have a polynomial in the numerator and one in the denominator. This is also a polynomial, even though it's a constant. It's a boring one. And a polynomial up here. But all we have to have is 1. As a matter of fact, just having one denominator that is non-zero is a rational equation. But of course, when the denominators are all whole numbers or integers, they're easier to take care of. So what we want to do, after I write this down, 3x minus 1 over 3 minus 2x, where x minus 1 is equal to x. We can do things in any order we want. But first, let's find the values where the denominators can equal to 0. And you only have to worry about the denominators that are polynomials with a variable term. So x minus 1 is equal to 0 when we just solve for x, when x is equal to 1. So what we just learned is that we cannot have x equal to 1. So at the very, very end, you have to look up here. If we were to have a possible solution with x equal to 1, then we would have to say there is no solution because we cannot have x equal to 1. I'm not really happy with that. I'll just use the same color. X cannot be equal to 1. So the first thing we want to do, or I guess now the second thing we want to do, is we have to find the LCD of 3 and x minus 1. Now there's a cool thing about finding the LCD of 3 and x minus 1. The LCD of two prime numbers, like 5 and 3, is always their product. So 3 is a prime number. It's an integer that is prime. And x minus 1 is a prime linear polynomial. So the LCD is simply 3 times x minus 1. So we're going to multiply both sides of our rational expression. I'm going to go ahead and kind of get rid of this 1a here. I want some room to move. We're going to multiply both sides. By multiplying both sides by the LCD, 3 times x minus 1. 3 times x minus 1. Now don't let this bother you over here. I didn't literally need to put these in parentheses. These parentheses right here aren't needed, but actually I don't know why I did that. Here, I'll put some over there so we'll have I better write over there what I need to write. It's 3 times x minus 1. So that's our LCD. So here we go. Let's simplify it. So the simplification's really easy. We're just going to use distribution again, where we literally distribute our term. It's on the outside to each of the inside terms. So 3 times x minus 1 divided by 3 is the same as x minus 1 times 3x minus 1. So let me say that again. 3 times x minus 1 times 3x minus 1 divided by 3 is the same as 3 divided by 3, which is 1, times x minus 1 times 3x minus 1. So in other words, in this first term, the 3's cancel out. And all I have is x minus 1 times 3x minus 1. So I just cleared the denominator in the first term. Now over here, I've got a minus sign. I'm going to multiply 3 times x minus 1 times 2x divided by x minus 1. So the x minus 1 terms cancel out, and I have 3 times 2x. And over here, all I'm going to do is rewrite this. This is x times 3 times x minus 1. So I'm going to write that as 3 times x minus 1. All I did was change the order of the products. So now I'm going to go ahead and simplify some more. So our only choice here is to expand. So I'm going to expand this using FOIL. So x times 3x is 3x squared. X times minus 1 is minus x. Minus 1 times 3x is minus 3x. And minus 1 times minus 1 is plus 1. So I just expanded this entire term right here. And this is going to be minus 3 times 2x is minus 6x. And this is going to be 3x times x is 3x squared. And 3x times minus 1 is minus 3x. Now here is a good time to kind of stop and look. Whenever you have two terms on both sides of an equal sign that are identical, meaning identical also in sign, they cancel out. In other words, if I were to subtract 3x squared from both sides, which you can do using the addition principle, both of those disappear. So I'm going to go ahead and do that. And the next thing I'm going to do is I'm going to combine like terms. So x minus 3x is minus 4x minus 6x plus 1 is equal to minus 3x. So minus 4x minus 6x is minus 10x plus 1 is equal to minus 3x. So I'm going to move the minus 10x term to the other side. And when I do so, it changes the sign. So I have 10x minus 3x. So 1 is equal to 7x. So we're almost there. So I know how many 7x's are. I want to know how many 1x is. So I divide both sides by 7. So my answer is x is equal to 1/7. So I have to check. So I look up here and check. And I did not get that x is equal to 1 because x can't be equal to 1. So this turns out to be my solution. Okay. So not so bad when we have the case when the rational expression leads to a linear equation. Well, you're kind of lucky if you're modeling or looking at a problem where that's the case. Usually they're going to lead to a quadratic equation, and that's what we're going to look at here. So let's solve 3x plus 1 over x minus 2 plus 1 over x is equal to minus 2 over x squared plus 2x. So the first thing that we're going to do is find the LCD. So I'm going to write my problem over here, and then I'm going to go ahead and find my LCD. So I have 3 over x plus 2 divided by x minus 2 plus 1 over x is equal to minus 2 over x squared minus 2x. So we have to find the LCD of the denominators. That's one thing we have to do. And the other thing is find values of x that make the denominators 0. Well, you can do these in any order, but what I want to do is I want to simplify my original one step before I do either of these two things. It will help in both. X minus 2 is prime. X is prime. Is x squared minus 2x prime? No. I note somewhere that x squared minus 2x, the greatest common factor is x, so that's equal to x times x minus 2. So I'm going to rewrite my expression with that simplification. You can do that at any point, and I'm not well enough organized that I have to do everything always at in the same order. If you are, then you decide which order it is and you do it. Notice that I put the minus in front kind of even with the division bar. That's fine because they're equivalent. So now let's find the LCD. So what we do to find the LCD is we look at all of the prime factors. So I have x minus 2, that's prime. X is prime. And x times x minus 2, well, those are two factors and they're already up there. So now I look at how many times they occur. In my first denominator, x minus 2. In my second denominator, x. And then in my third denominator, x times x minus 2. So how many times does x minus 2 occur in my first denominator? One time. How many times does it occur in my second denominator? 0 times. How many times does it occur in my third denominator? 1. How many times does x occur in my first denominator? This is x minus 2. I'm asking, does x appear in a factor in x minus 2? And it does not. But of course it appears in a factor there, and it appears in a factor there. So the LCD turns out to be our prime factors, x minus 2, raised to some power, which we're going to find out, times the other prime factor, x, also raised to some power. Well, what do I find in these boxes? How do I find what number to put in these boxes? Well, I look at my x minus 2 row, and I take the largest value that appears here. So that's 1. When I look now for this box here, I look in my X row and I take the largest value. So my LCD is equal to x minus 2 times x, or if you prefer to write it as x times x minus 2, which actually turns out to be the factorization of our second denominator. So we found the LCD. We can't forget to find out the values of x that make the denominator 0. Well, you can do that just by looking at the LCD. If you do it first, our LCD turns out to be x times x minus 2. Set that equal to 0, so that gives x is equal to 0, or x minus 2 is equal to 0, which implies x is equal to 2. So I take note over here. What is forbidden as solutions? We cannot have x cannot be equal to 0 and x cannot be equal to 2. Now you don't necessarily have to use the slash equal sign. If you want to just say, okay, x equals 0, x equals 2, my solutions can't be that, that's fine. Or you can say x cannot be 0, x cannot be 2. However you want to write that information. So we found values of x that make the denominator 0, and we found the LCD of the denominators. So what we're going to do here is we're going to multiply the entirety of both sides by that LCD. So you have to enclose, especially on the left-hand side, the entire thing in parentheses. I'm going to go ahead and enclose both sides in parentheses. And remember to keep the equality. We have to multiply both sides by the same amount. So let's see what that simplifies to. So x times x minus 2 times 3x plus 1 divided by x minus 2. Well, the x minus 2 terms cancel, and I'm left with x times 3x plus 2. That has to be put in parentheses. So x times x minus 2 times 1 over x. Well, the x's cancel now, so I'm left with x minus 2 times 1, which is just x minus 2. You can put that in parentheses if you want, but it doesn't matter. Over here, notice that the x times x minus 2 up here is the same as the denominator here. You could write it that way if you wanted to. So that whole thing just cancels out. So I have minus 2. Well, that's kind of nice. Now it's just an algebraic sprint to the end. So notice immediately that I have a minus 2 on both sides. So those are going to cancel. And what am I going to have left? I'm going to have x times 3x plus 2 plus x is equal to 0. Remember, they become zeros. The 0 over here I have to write down. I don't have to write down the 0 here because when I'm adding these other two terms to it, they don't change. So now let's go ahead and solve this. We can all solve this by now. We're going to use distribution here. X times 3x is 3x squared. X times 2 plus 2 is 2x. Plus x is equal to 0. So let's go ahead and collect like terms on the left-hand side. So that gives me 3x squared plus 3x is equal to 0. So now we factor out the GCF. And the GCF, the greatest common factor, is 3x. So I'm going to factor out 3x. So 3x squared divided by 3x leaves me 1 power of x. And 3x divided by 3x leaves me 1. Oh, how nice that was. I didn't even have to do quadratic equation or anything. It factored really nicely. So now I just use the zero product factor theorem. So that tells me 3x is equal to 0, or x plus 1 is equal to 0. So this implies, dividing both sides by 3, 0 divided by 3 is 0, and 3x divided by 3 is x. So this implies x is equal to 0. And this implies x is equal to minus 1. So at this point we have to run over here and see what is in our forbidden list. X can't be equal to 0, or x can't be equal to 2. So that means what I have to do is exclude that value and declare that really our only possible solution is x is equal to minus 1. And you really should go back and check it to make sure it does work. But in this case, I think that they always do work. Right offhand, I cannot imagine a case that they don't, but it's possible. And one of the reasons is we've already excluded the values that cannot possibly work. So this is our answer, and we're ready to go to the next problem. So the next problem is an applied problem. So I'm going to stop right now and talk a little bit more about this particular example it's the example given in the book. This worked out really, really nicely. But sometimes you might have to use, it's not going to reduce down to a really nice quadratic equation like we have right here. This is just a really, really nice quadratic equation to solve. You may have to use the quadratic formula in your homework, or you can always try to sharpen your factoring skills and try to factor them. If it doesn't factor, you've got to use the quadratic equation. If you see a homework problem that is really complicated and you think it's unfairly so, give me the heads up. I don't have time to work through all of the homework problems, and after all, my math lab changes the numbers for you all the time. So let me know, and I'll work it out for you and do something to make up for it. Probably just say, okay, I don't know what I'll do, but feel free to let me know if that's the case in any homework. I try to look at them and try to choose ones that are okay. Now, having to use the quadratic equation to find x is not a complication. The complication I think that would occur, I can't imagine one right at this case. So we have a work rate problem. So in this case, a rate, let's think about what a rate is by looking at some examples. A rate. Well, what about this rate? 70 miles per hour. Suppose you were looking at a sorting machine that could sort 1,287, what would you be sorting in parts per 1 hour. That's a rate. So in general, a rate is a ratio. But the number in the top normally has 1 unit, and the number in the bottom usually has a different unit. So 70 miles. Miles and hours are not the same. So when I say unit, I meant unit of measurement. So this is a work rate problem. So the rate of work is usually how many jobs, just like over here, jobs per hour or some other time reference. It could be seconds, it could be milliseconds. Think about, for you computer geeks out there, I am one too, but especially you gaming geeks, I am not. And you think about, oh, I want a fast processor. You want to know how many operations per second that processor can do. That's a rate. So how are we going to do this one? Well, first we're going to read through it as always. We're going to make a table from what we're going to do. And first, I guess what we have to do is find out what our rate is. And I've already told you it's going to be jobs per hour. That's our rate. So let's read the problem. One printer can do a job twice as fast as another. Working together, both printers can do the same job in 2 hours. So that's the reason I know it's jobs per hour. How long would it take each printer working alone to do the same job? So you're just locking up, so I have no idea. Why don't you just write it in Greek? I'd be okay. Well, let's actually look at our 3 parameters. Let's make a table. We have printer 1 and printer 2. So one of these, we're going to have to decide what our variable is. Now I'm going to say let x represent the rate for printer 1. Now you could have chosen printer 2, but I chose printer 1. And why did I choose it here? Because that's what I previously chose. And we're going to make a table. And that table is going to have how many columns? That's always the question, right? It's going to have 2 rows. But how many columns? Well, the columns are going to come from this factor. We have R is equal to J over T, where T stands for time. So I'm going to put J for the number of jobs, T for the time in hours, and R for the rate. And remember that R is J divided by T. Let's start filling in from what we've decided. I've already decided to let x, my unknown, represent the rate for printer 1. So the rate for printer 1, not the rate, but the time, sorry. Because that's how long. It's not the rate that we're looking for, but it's the time. Time. Easy enough correction. So x represents the time for printer 1. And what will be the time for printer 2? It can do the same job in twice the time. So if printer 1 can do a job twice as fast as printer 2, then if x is the time it takes for printer 1, it can do it in 2x. So how many jobs are they doing? This is 1 job per hour, right? So the rate, J divided by T, for the rate of printer 1 is 1 over x. And the rate of printer 1 is 1 over 2x. So I've got all of the tables up there, but we're not quite done. So there's a bit of information here that we don't have. So if I look at the rate of printer 1 and I add it to the rate of printer 2, I get how long it takes both of them to do it. And that is a rate of 1. Turns out to be 1/2 because it can do it twice as fast. Working together, both printers can do the same job in 2 hours. So that's one job over 2 hours. Twice as fast is where I get my 2x. Sorry if I misled there. So x is how fast printer 1 does. Printer 2 can do it twice as fast. And since they can do the same job, so the rate is one job over 2 hours. So the rate of printer 1 is 1 over x plus the rate of printer 2, 1 over 2x is equal to 1/2. And there's our equation. Now once we solve for x, I will have immediately how long it takes printer 1 to do it alone. And then when I plug in the value of x and multiply it by 2, I'll get the time it takes for printer 2. So what is the LCD here? So the LCD of x, 2x, and 2, I'm hoping you can see that the LCD is equal to 2x. So what values of x cannot be allowed? We'll set the LCD equal to 0, and that implies x is equal to 0. So I'm just going to keep that in mind, that x cannot be equal to 0 when I'm done. So as always, we're going to multiply both sides of our equation by the LCD. How do we know the LCD is 2x? Well, x is prime. 2 times x is 2. That's prime times x. So right there we go. We have x and 2. Those are the prime factors that occur in my, these are PFs. PF stands for prime factors. I have one denominator, which is x. The other is 2x. And the last one is 2. How many times does x appear in this denominator? Once. How many times does it appear in 2x? Once. How many times does it appear in 2? Not at all. How many times does 2 appear in the first denominator? None. It's a factor. How many times does 2 appear in the factor in the second? 1. And 1 in the last. So remember, my LCD is my prime factors, 2 raised to some power times x raised to some power. What is that power? For 2, it's the largest number that occurs in this row, and that's 2 to the first. For x, it's the largest number that occurs in that row, which is 1. So it's 2 times x, and that's how we got it. So we're going to multiply both sides by 2x and 2x. So when we do so, we're going to get 2x times 1 over x. The x's cancel out, and I get 2. 2x times 1 over 2x. Well, the 2x's cancel out, and I get 1. How nice is that? And the 1/2 times 2x, the 2's cancel out, and I get x. Are you kidding me? Look at that. So I have 3 is equal to x. So it takes printer 1 3 hours. So printer 1 takes 3 hours equal time for printer 1. And for printer 2, it takes 2 times 3 hours, which is equal to 6 hours, is the time for printer 2. So that one was not so bad. So the point is you try to make a table. I think perhaps the hardest place here was coming up with the 1/2, because I know that they're both working together. So the rate of printer 1 plus the rate of printer 2, what is it equal to? But it tells you right there they do the same job in 2 hours. So it's job per hour. So this has to be a rate over here. Since this is a rate and this is a rate, this has to be a rate too. Otherwise they couldn't be equal. I can't add 2 rates and get something else that is not a rate. So rates are jobs per hour. So they do the same job one job in how many hours? 2 hours. Okay. Ooh, yeah. So here we go. So now we're going to look at another type of problem that you should have encountered in intermediate algebra, and you're going to re-encounter it again. Now I'm going to introduce the power property that's going to help us solve these. So it's an interesting property, and we have to read it through very carefully. So if P and Q are algebraic expressions, not equations, but expressions. So you can imagine P being a polynomial and Q being a polynomial in the exact same variables. Then every solution of the equation, P is equal to Q, is also a solution to the equation P raised to the nth power is equal to Q raised to the nth power. So this is what I'm saying here. If I raise both sides of my equation to the same power, like 2 or 3 or 4, then any solution to the original equation is also a solution to the modified equation. So what's the big deal? The modified equation may have more solutions. It's certainly going to have the original solution, but it may add some more. So the thing here is, for each of our solutions, we have to check them. You have to check them. There's no getting out of it. Here's kind of like my mnemonic to do it. Square your way out. Now square should be put in scare quotes, because it could be we cube our way out or raise it to the 4th power. But usually it's going to be squaring our way out. So our first step is going to be isolate the radical on one side of the equation. Raise each side of the equation to a power that is the same as the index of the radical. What's the index? The value of n in the symbol, the nth root of x. When n is omitted and it's not written there, it's assumed to be 2. So that the radical is eliminated. Recall, also, we'll use this later on, the nth root of x is the same as x raised to 1 over n. If the equation contains a radical after this, repeat steps 1 and 2. So I guess maybe step 1 is isolate one radical on one side of the equation. And we'll see, I think, examples of both of these. So right here, we're going to solve an equation containing a square root. So my equation is x minus the square root of 15 minus 2x is equal to 0. So I'm going to take, since there's a minus in front of this radical sign, I'm just going to take the entire radical, including the minus. I'm going to move it over here. So basically I'm adding the square root of 15 minus 2x to both sides. So that's going to give me x is equal to the square root of 15 minus x. So the unwritten index here is 2. So my next step is we're going to raise both sides to the power of the index. Or to the value of the index, I guess is the better way to say that. And the index is 2. So this gives me x squared is equal to, when I raise both sides to the value of the index. So on the next simplification, I get x squared. Well, 15 minus the square root of 15 minus x squared, that's the way I can get the 15 minus x out from underneath the radical. I get rid of the radical. Oh, so that's not so bad. So now I want to turn this into a quadratic equation. So that means I'm going to move all of these terms on the right-hand side to the left-hand side. And I'm going to try to factor. One of the reasons I'm going to try to factor this is because it's a monic polynomial, degree 2 polynomial. The leading coefficient is 1. So coming over here, this is my way to do it. We make our little tic-tac-toe board, or whatever you want to call it. We want x squared there. Then I go and I write the constant term together with its sign. And in the last bottom corner, I write the middle term. Now, this is going to be easy to fill in. I have to put an x here and an x here. Then x times x is equal to x squared. Satisfied. Now I have to do two values multiplied together that give me minus 15. So minus 5 and 3 is a possibility, but I'm going to choose minus 3 and 5. So minus 3 and 5 gives me minus 15. So now comes the checkpoint. We multiply down this way. Minus 3 times x is minus 3x. And 5 times x is plus 5x. I'm just now seeing that I forgot to put a 2 right there. That's supposed to be a 2x. Sorry if you guys saw that earlier. I eventually get to it. So basically when I copied this radical down to here, I forgot to write the 2. I have placed it in there now, so we're going to go on. So that's what I want. I immediately realized right here, as I already have in my notes, that it can be factored, and minus 3x plus 5x is equal to 2x. So what is its factorization? Trust me, people, you ought to see some of, in graduate class, professors make mistakes like that constantly. X plus 5. It's common. It's a lot to keep track of. X minus 3. So, this means x plus 5 is equal to 0, or x minus 3 is equal to 0. Well, this first implies that x is equal to minus 5, and the second implies that x is equal to 3. So we have two solutions, and here's the big deal. We must check both. And that's the like, oh, I just solved it, I'm done, can I go on? Yeah, I wish you could, but the power property, the property I introduced you to at the very beginning, forces us to do this, because we may have got an extra equation. So let's look at the original equation. I have x minus the square root of 15 minus 2x is equal to 0. So let's check with x is equal to 3. So let's plug in 3. Two times 3 is 6. Let's check to see if is that equal to 0. Well, that gives me 3 minus the square root of 9. And that's 3 minus 3. So we get it is equal to 0. So this one checks. And I'll let you check with the x equal to minus 5. I have in my notes that it actually does work as well, but I'm not, you saw what I did there. You just have to start with this step right here and plug in 5 and see if you get 0. Okay, so the next problem. Oh yeah, there's one of these bound to happen, right? So solving an equation containing 2 radicals. 2 radicals with a constant out here. Well, thankfully, these problems have been created so that the algebra is not too tricky. You know, I always am wondering if they're assuming real valued solutions. The book doesn't say anything to check to see if your value of x makes either of these square roots a complex number. In which case, if they wanted only real valued solutions, you would have to eliminate those as well. But they don't even mention it to my recollection. So we're not going to worry about it either. So here, and this is the weird thing about this, all of the difference in the world as far as complication goes occurs with how you proceed to do this. So what I'm always going to tell you to do is whenever there is a radical sign with a negative in front of it, you want to move it to the other side. That means the first thing we're going to do is, the best we can do is just isolate one of these. So I'm going to isolate the first radical. So that's going to give me 2x plus 3 is equal to 1 plus the square root of x plus 1. Also recall the formula a plus b squared is equal to a squared plus 2ab plus b squared. Believe it or not, I mean, Jeopardy is reruns right now because of COVID-19, but literally this very question was asked as a Jeopardy question. Like, do the math. And they gave a plus b in parentheses squared is equal to, and they wanted this. And yes, someone got the answer. Yeah, they sure did. More than one person rang in, too. One person beat the other one to it. So what are we going to do? We're going to raise both sides to the index of these radicals, and the index is 2. When we do so over here on the left-hand side, that's going to get rid of the radical sign. But over here, when I use this formula, 1 plus 2 on the square root of x plus 1 plus x plus 1. So this is my a plus b squared. My a is 1, so a squared is 1 squared. My second term is 2 times a times b, so 2 times a is 1. 2 times a is 2 times b gives me 2 on the square root of x plus 1, and b is the square root of x plus 1, so when I squared it, I got x plus 1. So now what I'm going to do is I'm going to be able, and I'm going to have to isolate this radical by itself. That means these terms have to move over. So that's going to give me 2x plus 3. And 1 plus 1 is 2. So when I move 2 over, it becomes minus 2 is equal to 2 on the square root of x plus 1. So we're going to have to simplify this side over here. So that's going to give me 2x plus 1. Oh, I forgot to move the x over. So the x comes over and we get a minus. Let me help you out here. I didn't move all my terms over, I just moved the constant terms over. And we want to move the x over too, and when we move it over, it becomes minus. So then I have 2x minus x gives me x. Yeah, it would have been impossible if I allowed that mistake not to be seen, it would have just been impossible. So 2x minus x gives me an x, and a 3 minus 2 is 1. So x plus 1 is equal to 2 on the square root of x plus 1. And here I'm going to remind you of another exponent rule. So if I have a product a times b, and I raise it to the nth power, that's equal to a to the nth times b to the nth. I'm going to use it right over here. So what we're going to do is we got to square our way out of this until we don't have any radicals. Each time I'm squaring, I'm adding more solutions. So again, I'm going to use the formula x plus 1 squared is x squared plus 2x plus 1, because I have that special product memorized. And this is 2 times x plus 1 squared, so that by this formula, that's the same as 2 squared, which is 4, times the square root of x plus 1 squared, which is x plus 1. Oh, that it's beginning to look a little bit better, although I do see I'm going to have a quadratic equation I'm going to have to deal with. But we do have the quadratic formula, right? So it's just a simplification now. It's just algebra. X squared plus 2x plus 1 is equal to 4x plus 4. So let's move everything over. That's going to give me x squared plus 2x minus 4x plus 1 minus 4 is equal to 0, which gives me the quadratic equation x squared minus 2x minus 3 is equal to 0. Can we factor that? Something's telling me we can. No need for the quadratic formula here. I need x squared, then my constant term together with its sign, and then my middle term together with its sign. I have no choice but to put an x and an x there. It's monic, that's the reason. It might be. Many of you can do monic polynomials in your head. And for minus 3, I only have one choice, 1 and minus 3. So if this doesn't work, because 3 is prime, if this doesn't work, I guess I could do minus 1 and 3. That'll have to be, that's the only thing I can try. So this is x minus 3x, and x minus 3x is indeed 2x. So the factorization worked. Here are my two factors. Sorry, I can't really do that much better. So this becomes x minus 3. X minus 3 times x plus 1 is equal to 0. So that means x minus 3 is equal to 0, or x plus 1 is equal to 0. These are really easy to solve. That implies x is equal to 3, or x is equal to minus 1. So these are possible solutions. I absolutely have to check them because I squared 2 times. Check each one. So you go back and you look at the original one, and I'm going to let you do it. And it turns out that both of them check. Well, I'll do one of them. I'm just being really lazy today. It's a Sunday. I try to get all of your videos recorded before the start of the week, if at all possible. Some of you who want to work ahead appreciate it. Well, that's equivalent to our first equation. It's not exactly what it is. It's the second simplification step, but that's okay. It's absolutely equivalent. I've not raised anything to any power, so I don't have to worry. So let's check x equals 3. So this is going to be the square root of 2 times 3 is 6. 6 plus 3 is 9. This is going to be the square root of 3 plus 1 is 4, so it's the square root of 4. So the square root of 9, remember there is no negative here, so it's the positive root, is 3. And the square root of 4 is 2. So 3 is equal to 3, so that one checks. Equally, you could check x is equal to minus 1. So that's going to give me minus 2 plus 3. So minus 2 plus 3 is 1, and the square root of 1 is 1. And minus 1 plus 1 is 0, so the square root of 0 is 0, so I have 1 is equal to 1. So both of them turn out to check. Okay, getting close. So we're going to solve equations with rational exponents. So here are some things we've got to remember, some hints on how to solve these. So remember that the nth root of x, I repeat that again, is equivalent to x raised to the 1 over n power. And also recall that if x squared is equal to b by the square root property, means x is equal to plus or minus to the square root of b, which we can now extend to the following. If x is raised to an even number, so 2 times any integer is even, and these are going to be positive, so 2 times any natural number is going to be an even positive number. So if x to the 2n is equal to b, then x is equal to plus or minus b raised to the 2n divided by 2, which is the nth power. So that plus or minus will be something that we're going to have to deal with. But the general rule for solving equations with rational exponents is to raise each side to the reciprocal of the original exponent. So let me, I just started Chrome. I want to bring up this. Let me show you one other thing here. I didn't write it down, I didn't type it up, but I want to remind you of some really handy things. X raised to the power a divided by b is equal to x raised to the 1 divided by b power raised to the 8th power. 8th power. But it's also equal to x to the 8th power raised to the 1 over the b power. Why is that? Because we have the power product rule of exponentiation. A raised to the nth power raised to the nth power is equal to a raised to the m times n. So 1 divided by b times a is a divided by b. And a times 1 divided by b is a divided by b. So that's going to be important. And also, the following, assuming b is not 0, the reciprocal of a divided by b is b divided by a, and their product is 1. So that's one of the reasons where I said that about the reciprocal, is that's going to be the trick we're going to use to get, we have 5x, so I know what 5x is equal, how much is 1x? Well, I'm going to turn out I'm going to have x to the 3/5 is equal to something, but I want to know how much x to the first power is. So in order, the analogy of that is raising it to the reciprocal. So here, we're going to do this two ways. Just one way, actually. So I have x raised to the 3/5 power is equal to 27. Now 27 is equal to 3 to the 3rd power. And I'm going to write it as 3 to the 3rd power. Why? Because the fact that the numerator in this exponent is 3 is going to be important. So I'm just going to do for my next step is just rewrite 27 as equal to 3 to the 3rd power. So all I'm redoing there is rewriting 27 to some other form that is equal to 27. So now what we're going to do is we're going to raise both sides to the same power. And what power is that? Well, my exponent, my rational exponent is 3/5, and its reciprocal is 5/3. So I'm going to raise both sides to the 5/3 power. Since I chose the reciprocal of 3/5 to be my new power, that's just going to leave me with x here. Because 3/5 times 5/3 is x to the 1th power, which is just x. But over here, I'm going to use what I just told you. 3 to the 3rd times the 5/5 is equal to 3 to the 3 over 1 times 5 over 3. So those 3's are going to cancel out. So x is equal to 3 to the 5th power. In other words, 3, writing it as 3 times 1, I'm just multiplying 3 over 1 times 5/3. The 3's cancel, and I have 5. So x is equal to 3 to the 5th. So all you have to do is figure out what 3 to the 5th is. I know what you're going to do. You're going to break out your calculators. I'm going to do it for you. I've already got it figured out. X is equal to 243. And no, there's no way for you to check this. The only way for you to check this is if you could go back to the original equation and take the 3/5 root of x. And you can't do that. A calculator will do that for you. So we are declaring that this is my solution. However, B is going to pose a little bit of thinking. So I have x minus 4 to the 2/3 is equal to 16. So since this is 2 up here, I'm going to write 16 as the power of 2. It's 2 to the 4th. 2, 4, 8, 16. But here we want to look at our power. I'm going to multiply by the reciprocal of 2/3, which is 3/2, which is the same as 1/2 to the 3rd power. So in essence, I'm taking a square root somewhere. So if you understand why and why I made that connection, that's fine. If not, all you have to do is when you have the original power, if the numerator is even, then when you multiply both sides by the reciprocal of the power, you have to add a plus or minus. So that gives me the 2/3 times 3/2 cancel, and that gives me x minus 4. That's going to give me equal to plus or minus 2. 4 times 3 is 12. 12 divided by 2 is 6. Plus or minus 2 to the 6th. So 2 to the 6th is 2, 4, 8, 16, 32, 64. So x minus 4 is equal to plus or minus 64. That gives me two solutions. So let's take the top one first. That gives me x minus 4 is equal to 64, which gives me x is equal to 64 plus 4, which gives me 68. Now let's take the bottom one. X minus 4 is equal to minus 64. So that gives me x is equal to minus 64 plus 4, which is minus 60. So my solution set is minus 60 and 68. I think that's it. Oh, no. We have some other things to do. But that's okay. These aren't so bad. So, an equation in quadratic form is one which can be written as AU squared plus BU plus C is equal to 0, where clearly A is not equal to 0, and U in this case stands for an algebraic expression like a polynomial. So for those of you who have to take calculus, this is kind of like an early entry of what's called a U substitution, but you're doing a substitution of a different type and for a different type of solution, but you're still doing a substitution. So let's look at this. So the first thing you have to do here is you have to decide what your U is going to be. So here, I'm going to rewrite the first equation. Instead of x plus 1 to the 3/2, I'm going to write it as x plus 1 to the 1/3, and all of that is going to be raised to the second power. 1/3 times 2 is 2/3, and that's what I have there. Then I have x plus 1 times the 1/3 minus 2 is equal to 0. So now I'm going to observe if I let U equal x plus 1. That's a bit of information that we have to write down and remember to come back to. Then this can be written as, it's not x plus 1, x plus 1 to the 1/3. There we go. So let U equal x plus 1 to the 1/3, and that's stuff that we want to remember. Then I can rewrite this as x plus 1 to the 1/3 is U, and that term is squared. X plus 1 to the 1/3 is U, minus 2 is equal to 0. So this is a quadratic equation in the variable U. It's kind of cool. And this can easily be factored. This just simply factors. I'm going to let you all do this on your own. Is U minus 2 times U plus 1. And that's equal to 0. So now I have to solve for U. This implies U minus 2 is equal to 0. or u plus 1 is equal to 0. That means u is equal to 2, or u is equal to minus 1. Okay, but I'm not done, because our original equation is in the variable x, and I have a solution in u. But that's when we come up here and we use this bit of information. Let u be x plus 1 to the 1/3. So here we go. I'm going to take two different cases. I'm going to let u be equal to 2. So 2 is equal to x plus 1 to the 1/3. So how do we solve that? Well, my exponent is 1/3, and the reciprocal of 1/3 is 3. So I'm going to raise both sides to the third power. Two to the third is 8. 2 times 2 times 2. And 1/3 times 3 is 1, so that gives me x plus 1. Oh, how nice. So I'm going to move the 1 over and get x is equal to 7. And for the second one, I have u is equal to minus 1. So minus 1 is equal to x plus 1 to the 1/3. So again, we're going to raise both sides to the third power. And that gives me minus 1 times minus 1 is plus 1 times minus 1 is minus 1. So I have minus 1 over here. And x plus 1 to the 1/3 raised to the third power is equal to x plus 1. So all I'm going to do is move the 1 to the other side. So 1 minus 1 is equal to x. So minus 2 is equal to x. So those are my two solutions. 7 is equal to 7. Seriously, can't? 7 is equal to x. So x is equal to 7, or x is equal to minus 2, and those are solutions. Okay, now I do know we're on the last problem. Oh, literally that was the last problem. So this takes time. Just algebraic skills, they seem, when you look at a problem like this right here, your normal algebraic skills fail you. But notice that the solution was just a replacement value. If I let u be equal to x plus 1 to the 1/3, then this becomes a quadratic equation. I can solve for u and then set u equal to x plus 1 to the 1/3 and use regular techniques, because u is going to be an actual number. At any rate, that's all I have for today.